So we are looking at learning objective 7 in unit 5. So to explain the nature of electromagnetic radiation. So what is electromagnetic radiation? Electromagnetic radiation is a form of energy that travels through space at the speed of light, which is 3 times 10 to the 8th meters per second. This has a dual nature, which means that it acts as both a wave and a particle. We call the particle a photon. So a particle of light is called a photon. There's two quantities that are in electromagnetic radiation. One of them is the wavelength, and this determines the energy of the wave or the light. The unit here is meters, or sometimes we use nanometers. So just depending on if it's a lot of times the wavelength is very, very, very short. So we use nanometers for that. The abbreviation for wavelength is lambda. Is the Greek letter, looks like an upside down Y. It's called a lambda. So if we have a short wavelength, that means we have high energy. And if we have a long wavelength, then we have low energy. So again, energy that travels through space at the speed of light is electromagnetic radiation. It has a dual nature. It is both a wave and a particle, which we call a photon. It has the quantity of wavelength, which determines the energy, and it is measured in meters or nanometers. It is abbreviated as lambda, the Greek letter lambda. The second quantity that light has is a frequency. So frequency is the number of cycles or crests that pass through a stationary point in 1 second. Its unit is usually measured in hertz, which is Hz. This is also 1 over seconds. So if you see hertz, it's really 1 over seconds. The abbreviation for frequency looks like a V. It's really the Greek letter nu. So it is nu. So the formula between wavelength and frequency, to get from wavelength to frequency, you use C is equal to the wavelength times the frequency. So C again is the speed of light, which is meters per second. Lambda here is the wavelength. It's measured in meters. You have to be in meters to use this. And then V, this nu, is frequency, which is 1 over seconds. So if you take your meters times your 1 over seconds, you get meters per second. So then some relationships between energy and wavelength and frequency. So a long wavelength, so long lambda, is equal to a low nu frequency, which is also equal to a low energy. And then a short wavelength is equal to a high frequency, which is equal to a high energy. Okay, so then we have this electromagnetic spectrum, which here would be your high energy. This would be your low energy. So low energy, low frequency, long wavelength, high energy, high frequency, short wavelength. So if you're looking at something like this, and what is light and what is electromagnetic radiation, there's a whole bunch of different forms to electromagnetic radiation. So we have if you listen to the radio in your car, you are listening to radio waves, which are some of the lowest energy, lowest frequency, longest wavelength types of light that we have, or electromagnetic radiation. Then we move from radio waves into microwaves, which are what we use in the microwave to heat up food, which we're getting into a little bit more energy here. So more energy, increasing energy this way, decreasing energy this way. And then we get into infrared, or IR. Okay. So this is like your infrared goggles, that type of thing. They measure kind of heat waves that are coming off of things. And you can see in the dark with infrared. Then you have your visible. So this is the visible spectrum. This little teeny tiny little spot right here is what we can see. That is all that we can see. So anything outside of this realm would be considered dark to us. We wouldn't be able to see it. And within the visible spectrum, you have all the colors of the rainbow. So red would be here. You have orange, yellow, green would be right in the middle. Blue, indigo, and violet. So your red light is the lowest energy, whereas your violet light is your highest energy that you can see. So, and on the bottom here, you can see that this is from 750 nanometers to 400 nanometers. That is what we can see. That is all that we can see. We get into the UV spectrum, which is ultraviolet. So this is the ultraviolet. It's a little bit more energy. It can cause some problems within the DNA at the cell level. So we're getting into more energy here. We actually protect ourselves from UV, from the sun, by putting on sunscreen. So we can block it by using sunscreen. Then we have X-rays. So X-rays are what we use to look at the bone and see if it's broken. We use X-rays in a lot of different ways just to kind of be able to see what's going on at the bone level. So these are a little bit more penetrating. The light actually penetrates through the skin into the bone and then bounces back. So with X-rays, we protect ourselves by using a lead plate or a lead shield to protect our organs and that type of things from the X-ray. The final type of light that we talk about in this class is gamma. And gamma are very high frequency waves and radiation. These are going to be from cosmic, so like cosmic rays and that type of thing that are like bounced off of our atmosphere. That's what gamma rays are. So we really protect ourselves from gamma rays. But also we use X-rays and gamma rays in radiation therapy and cancer. So there is some good to these as well, because we can like pinpoint an area that needs radiation, and then we use radiation therapy on cancer cells and that type of thing. So this is electromagnetic radiation. You are in contact with this stuff all the time. It is not anything that, so you have some sort of radiation that is always bouncing off of you all the time, whether they be radio waves, microwaves, infrared, or something that you can see. So one thing to remember is that the relationships between wavelength and frequency, and the wavelength and energy, that type of thing. So as you increase your wavelength, you are decreasing your frequency, which means that you're also decreasing your energy. As you decrease your wavelength, you are increasing your frequency, which is also an increase in energy. Okay, so wavelength and frequency have an inverse relationship, or an indirect relationship, you could say. And then frequency and energy have a direct. So important things to kind of remember here. You have nothing to be afraid of from radiation. You're constantly being bombarded with radiation all the time. So can these things cause cancer? Yes. But it really just depends. So this was learning objective 7, unit 5, to explain the nature of electromagnetic radiation. So electromagnetic radiation are just the particles of light.